round sphere. It has a radius A and a uniform charge density rho, a volume charge density. The sphere is not centered at the origin, so the sphere is off from the origin, and the position vector relative to the origin is B. Show that the electric field inside the sphere is rho times r minus b over 3 epsilon naught. So to get started, let's ask what we're trying to find. We're trying to find the electric field inside the sphere, and I think I'll just redraw it so I don't get that guy too messy. So here's my sphere. Here's my coordinate system. Here's where I'd like to find the electric field at some position inside the sphere. So I'm going to call this vector r. I already know that the vector to the center of the sphere is b. So now the distance from the center to some point out from the center, I'm going to call that r primed. Okay, so now what I have is a set of vectors on my picture. B, this point right here is the center of the sphere. R primed is a vector to some place inside the sphere, and R and B relate that vector to the origin of our coordinate system. So let's ask, we're trying to find the electric field as a function of R. Let's ask first, could we find the electric field as a function of R primed? And I'm going to say yes, we can find that because R primed is relative to the center of the sphere. And that's a problem we know how to solve. Then the other thing that we can see, B plus R primed equals R. That's just a simple vector addition. This vector plus this vector gives us this vector. So let's add in that little note, and B plus R primed equals R. So what that means is that R primed equals R minus B. So our strategy here is let's find the electric field of this sphere relative to its center, and then we'll just use a translation that R primed is R minus B to find the electric field in terms of R. So let's start with the electric field relative to the center of the sphere. I'm going to redraw that sphere again. There's the center of the sphere. I'm going to try and find the electric field some distance r primed from the center of the sphere. We'll write down Gauss's law. The net electric flux is the integral of E dot dA equals the charge within the Gaussian surface divided by the constant epsilon naught. Our Gaussian surface is a sphere within our insulating sphere. Let's find the two sides of Gauss's law here. So the integral of E dot dA is the integral of E times dA times cosine of the angle between them. Our electric field comes out everywhere. There's the electric field. A little bit of an area vector also comes out everywhere. Those guys are parallel, so it's E times dA times cosine 0. The electric field, when we're a constant distance away, is a constant value, so E comes outside of dA, leaving us with E times A. A is the area of our Gaussian surface. Our Gaussian surface is a sphere, and it has an area of 4 pi r squared, r primed squared. There's that side of the integral. What about the other side? What is Q inside? Q in is the amount of charge within the Gaussian surface. The amount of charge within the Gaussian surface would be the charge density times the volume of the Gaussian surface. So that would be the density times 4/3 times pi times r primed cubed. So there's the two sides of our Gauss's law. Let's plug in this for this side, and see what we get. So E times 4 pi times r primed squared equals rho times 4/3 times pi times r primed cubed over epsilon naught. 4 pi's on either side cancel. R squared here divides into r cubed to leave us with r primed. So E equals rho times r primed divided by 3 times epsilon naught. Electric field is a vector and it has a direction. The direction of the electric field vector is radial. It points in the same direction as r primed. So E is equal to rho times r primed, 3 epsilon naught r primed hat. So that's a unit vector in the direction of r primed. R prime times r prime, the magnitude, times the unit vector gives us the vector r primed. Now for our very last step, let's remember that relationship we had between RB and R primed. R primed is R, take away B. So let's fill that part in right here. So there's our expression for the electric field of this sphere in terms of a vector relative to the origin of the system.